Hello everybody. Today we will be reading the paper Language Models are Unsupervised Multitask Learners by Alec Radford, Jeffrey Wu, Rewon, David Luan, Dario Amodei, and Ilya Sutskever. This is the GPT-2 paper and the lab is OpenAI, so you may recognize a couple of these authors from previous papers that we have read. Let's start off with the abstract. Natural language processing tasks such as question answering, machine translation, reading comprehension, and summarization are typically approached with supervised learning on task-specific datasets. We demonstrate that language models begin to learn these tasks without any explicit supervision when trained on a new dataset of millions of web pages called web text. When conditioned on a document plus questions, the answer generated by the language models reach 55 F1 on the COCA dataset, matching or exceeding the performance of 3 out of 4 baseline systems without using the 127K plus training examples. The capacity of the language model is essential to the success of the zero-shot task transfer, and increasing it improves performance in a log linear fashion across tasks. Our largest model, GPT-2, is a 1.5 billion parameter transformer that achieves state-of-the-art results in 7 out of 8 tested language modeling datasets in a zero-shot setting, but still underfits web text. Samples from the model reflect these improvements and contain coherent paragraphs of text. These findings suggest a promising path towards building languages processing systems which learn to perform tasks from their naturally occurring demonstrations. So the abstract is basically explaining that the claim of this paper is that they train one model to just predict the next word in a giant pile of internet text, and they never tell it how to answer questions or how to do tasks like reading comprehension, summarization, translation. And they just test it on all of these tasks anyways, and the model is just able to do them without any sort of fine-tuning and just picking up from the text that it has been given. So this is what they called unsupervised learning. Now, normally, if you want a model to answer questions, you have to collect a big set of questions with their answers and you train the model on all of those, and that is supervised learning. What they're saying here is that their model gets 55 on a question answering test called COCA, and it matches or beats 3 out of 4 systems that did get trained on 127K plus question answer pairs. And their model saw 0 of these question answer pairs, and it was still able to score similar results. So it gets these results without any of the task-specific training that these other models got. So let's start off with the introduction. Machine learning systems now excel in expectation at tasks they are trained for by using a combination of large datasets, high-capacity models, and supervised learning. Yet these systems are brittle and sensitive to slight changes in the data distribution and task specification. Current systems are better at characterized as narrow experts rather than competent generalists. We would like to move towards more general systems which can perform many tasks, eventually without the need to manually create and label a training dataset for each one. So they are setting up with a complaint about how machine learning normally works. Back in this day, systems were good for one specific task that you trained them for, but they were extremely brittle, and if you change the data a little or if you changed how you phrase the task, it completely falls apart. So they call these systems narrow experts. The dominant approach to creating ML systems is to collect a data set of training examples demonstrating correct behavior for a desired task. Train a system to imitate these behaviors and then test its performance on independent and identically distributed held-out examples. This has served well to make progress on narrow experts, but the often erratic behavior of captioning models, reading comprehension systems, and image classifiers on the diversity and variety of possible inputs highlights some of the shortcomings of this approach. So they're explaining that what they want instead is a generalist, one system that can do many tasks eventually without having to build and label a separate training set for every single one. And they name that the The standard recipe here is pretty fragile. You collect examples of the correct behavior, you train the model to copy that behavior, and then you test it on examples from the same distribution. Now, the phrase that they use here is independent and identically distributed, or IID. That just means the test data looks like the training data drawn from the same pool. The problem is that models trained this way break when the real world doesn't match this pool. So they point at captioning models, reading comprehension systems, image classifiers, and they say that these behave badly when the inputs get diverse. Our suspicion is that the prevalence of single task training on single domain datasets is a major contributor to the lack of generalization observed in current systems. Progress towards robust systems with current architectures is likely to require training and measuring performance on a wide range of domains and tasks. Recently, several benchmarks have been produced, such as GLUE and DECA NLP, to begin studying this. So, they think the reason these systems don't generalize is that we train them on a single task, on a single narrow type of data. So if you want generalization, you probably need to train and measure on a wide range of tasks and domains all at once. And they mentioned two benchmarks to do this, GLUE and DECA NLP. These are just collections of many tasks bundled together. Multitask learning is a promising framework for improving general performance. However, multitask training in NLP is still nascent. Recent work report modest performance improvements, and the two most ambitious Recent work reports modest performance improvements, and the two most ambitious efforts to date have trained on a total of 10 and 17 dataset objective pairs, respectively. From a meta-learning perspective, each dataset objective pair is a single training example sampled from the distribution of datasets and objectives. Current ML systems need hundreds to thousands of examples to induce functions which generalize well. This suggests that multitask training many need just as many effective training pairs to realize its promise with current approaches. It will be very difficult to continue to scale the creation of datasets and the design of objectives to the degree that may be required to brute force our way there with current techniques. This motivates exploring additional setups for performing multitask learning. Alright, so multitask learning means training one model on several tasks at the same time and hoping that it gets better at all of them. So they say that it's a nice idea, but in language it's barely been tried, and the biggest attempts so far was trained on 10 and 17 pairs, and the way they write a pair is data plus objective, meaning a data set and the thing that you want the model to do with it. Then they make a point that from a certain angle, each of these data objective pairs is just one training example. So modern models need hundreds to thousands of examples to learn a function that can generalize. So to make multitask learning actually work the normal way, you would need hundreds or thousands of these task setups, which need to be hand-built each. Now this doesn't really scale, so you cannot brute force your way there. The current best performing systems on language tasks utilize a combination of pre-training and supervised fine-tuning. This approach has a long history with a trend towards more flexible forms of transfer. First, word vectors were learned and used as inputs to task-specific architectures. Then, the contextual representations of recurrent networks were transferred, and recent work suggests that task-specific architectures are no longer necessary and transferring many self-attention blocks is sufficient. So they walk through the history really fast. The trend in languages has been pre-training plus fine-tuning. You pre-train a model with a lot of text first and then adjust it for your specific task. And over time, the amount of hand-built task machinery just keeps shrinking. So first, people started by just transferring word vectors. And then they moved on to transferring entire networks and the most recent finding is that you don't even need a task-specific architecture anymore. You can just reuse the same stack of self-attention blocks. And self-attention is the transformer mechanism, so the direction is pretty clear. You need less and less custom machinery per task. These sufficient methods still require supervised training in order to perform a task. When only minimal or no supervised data is available, another line of work has demonstrated the promise of language models to perform specific tasks such as common sense reasoning and sentiment analysis. Now, even those transfer methods still need some supervised training to actually do the task. But there is a separate line of work showing that language models with little or no task training can already do certain things like common sense reasoning and sentiment analysis. All right. Language modeling is also able to, in principle, learn the tasks of McCann without the need for explicit supervision of which symbols are the outputs to be predicted. Since the supervised objective is the same as the unsupervised objective, but only evaluated on a subset of sequence, this global minimum of the unsupervised objective is also the global minimum of the supervised objective. In this slightly toy setting, the concerns with the density estimation as a principal training objective is discussed in Sutskever et al. Are sidestepped. The problem instead becomes whether we are able to, in practice, optimize the unsupervised objective to convergence. Preliminary experiments confirm that sufficiently large language models are able to perform multitask learning in this toyish setup, but learning is much slower than in explicitly supervised approaches. So this is the theoretical hope that they have. If your text contains examples of a task, then the unsupervised goal is to just predict the next word over everything. Includes the supervised goal as a part of itself. So, in principle, a model that perfectly predicts text would also perfectly do every task that appears in that text. The supervised answer is a subset of the next word problem. Now, they call this a toyish setup, and they admit that learning this way is much slower than just training on the task directly. And the claim is it's possible in principle, and their experiments are clearly evidence, but they are not proof. While it is a large step from the well-posed setup described above to the messiness of language in the wild, Weston argues in the context of dialogue for the need to develop systems capable of learning from natural language directly and demonstrated proof of a concept, learning a QA task without a reward signal by using forward prediction of a teacher's outputs. While dialogue is an attractive approach, we worry it is overly restrictive. The internet contains a vast amount of information that is passively available without the need for interactive communication. Our speculation is that a language model with sufficient capacity will begin to learn to infer and perform the tasks demonstrated in natural language sequences in order to better predict them, regardless of their method of procurement. If a language model is able to do this, it will be, in effect, performing unsupervised multitask learning. We test whether this is the case by analyzing the performance of language models in a zero-shot setting on a wide variety of tasks. So they quote Weston, describing real text as language in the wild, which is because the internet is full of people demonstrating tasks just by doing them. They have no labels attached to them. So their speculation is that a big enough model will start to learn those tasks just because doing so helps it predict the text better. So now the plan is set. You train a language model, then you test it zero shot on a bunch of tasks, and then let's see what they trained it on. Training data set. Most prior work trained language models on a single domain of text, such as news articles, Wikipedia, or fiction books. Our approach motivates building as large and diverse a dataset as possible in order to collect natural language demonstrations of tasks in as varied of domains and contexts as possible. So most earlier work trained on one kind of text, like news, Wikipedia, but their whole thesis says variety matters, so they want a data set that's as big and as varied as they can make it. A promising source of diverse and nearly unlimited text is web scrapes such as Common Crawl. While these archives are many orders of magnitude larger than current language modeling datasets, they have significant data quality issues. Chin and Lei used Common Crawl in their work on common sense reasoning but noted a large amount of documents whose content are mostly unintelligible. We observed similar data issues in our initial experiments with Common Crawl. Chin and Lei's best results were achieved using a small subsample of Common Crawl, which included only documents most similar to their target dataset, the Winograd Schema Challenge. While this is a pragmatic approach to improve performance on a specific task, we want to avoid making assumptions about the task to be performed ahead of time. Now, the obvious giant source of text is Common Crawl, which is basically a scrape of huge chunks of the web, but they say that there is a quality problem with it, and a lot of it is junk. They quote earlier work calling a lot of these documents unintelligible. So raw web scrape is too messy. Now one fix that others used is to only keep the bits of Common Crawl that look like your target task. But that defeats the purpose here. They specifically don't want to assume which tasks they'll set on, so filtering the data towards a task is completely off the table. Instead, we created a new web scrape which emphasizes document quality. To do this, we only scraped web pages which have been curated or filtered by humans. Manually filtering a full web scrape could be exceptionally expensive, so as a starting point, we scraped all outbound links from Reddit, a social media platform which received at least 3 karma. This can be thought of as a heuristic indicator for whether other users found the link interesting, educational, or just funny. So this is how they built their dataset. They wanted web pages that humans had already decided were worth reading, and filtering by hand would cost a fortune, so instead they used Reddit, and they grabbed every outbound link that had at least 3 karma, and karma is basically upvotes versus downvotes. And the logic is, if a few humans upvoted a link, it's probably interesting or educational, and so Reddit's upvotes are doing the quality filtering for free. The resulting dataset, web text, contains the text subset of these 45 million links. To extract the text from HTML responses, we use a combination of the Dragnet and newspaper content extractors. All results presented in this paper use a preliminary version of web text which does not include links created after December 2017, and which after deduplication and some heuristic-based cleaning contains slightly over 8 million documents for a total of 40 GB of text. We removed all Wikipedia documents from web text since it is a common data source for other datasets and could complicate analysis due to overlapping training data with test evaluation tasks. Okay. They call the result web text. You start with 45 million links, and they pull the readable text out of the web pages. They clean it up, remove any kind of duplicates, and you end up with a bit over 8 million documents. And this is around 40 gigabytes of text. And one specific cleaning choice that they used is they used a cutoff. So they said no links after December 2017. So there is a clean date boundary on which the model has been set. Now, one careful decision is that they removed Wikipedia because Wikipedia shows up inside a lot of the test sets that they're going to evaluate on. So, if Wikipedia were in the training data and the test data, they couldn't tell if the model learned something or just memorized the test. So they remove it up front to keep the evaluation honest, and the instinct to worry about the overlap between train and test data, it comes back as a whole section later. Input representation. A general language model should be able to compute the probability of and also generate any string. Current large-scale LMs include pre-processing steps such as lower casing, tokenization, and out-of-vocabulary tokens, which restrict the space of modelable strings. While processing Unicode strings such as a sequence of UTF-8 bytes elegantly fulfills this requirement as exemplified in works such as Gillick et al., current byte-level LMs are not competitive with word-level LMs on large-scale datasets such as 1 billion word benchmark. We observed a similar performance gap in our own attempts to train standard byte-level LMs on web text. Now, the problem that they are solving is that they want a model that can handle literally any string of text that you throw at it. Normal models cheat a little bit. They lowercase everything. They break text into a fixed vocabulary of words, and any word they've never seen becomes a single unknown token. Now, this restricts what the model can even represent. One clean fix is to work at the level of bytes, the raw building blocks of text, because then you can represent anything. But they say that pure byte level models haven't been as good as word level ones on big data sets. Byte pair encoding (BPE) is a practical middle ground between character and word-level language modeling, which effectively interpolates between word-level inputs for frequent symbol sequences and character-level inputs for infrequent symbol sequences. Word-level for frequent and character-level for infrequent. Despite its name, reference BPE implementations often operate on Unicode code points and not byte sequences. This implementation would require including the full space of Unicode symbols in order to model all Unicode strings. This would result in a base vocabulary of over 130K before any multi-symbol tokens are added. This is prohibitively large compared to the 32K to 64K token vocabularies often used with BPE. In contrast, a byte-level version of BPE only requires a base vocabulary of size 256. However, directly applying BPE to the byte sequence results in suboptimal merges due to using a greedy function. Greedy frequency-based heuristic for building the token vocabulary. We observe BPE including many versions of common words like dog, since they occur in many variations such as dog with a full stop, exclamation mark, and question mark. This results in a suboptimal allocation of limited vocabulary slots and model capacity. To avoid this, we prevent BPE from merging across character categories for any byte sequence. We add an exception for spaces, which significantly improves the compression efficiency while adding only minimal fragmentation of words across multiple vocab tokens. Alright, so the middle ground is basically called byte pair encoding or BPE. And the idea is that common chunks of text get their own single token and rare stuff gets spelled out in smaller pieces. So frequent words, they stay whole, and rare words get represented in smaller parts instead. And so they run BPE on bytes instead of on characters, which keeps the starting vocabulary very small, only 256 bytes, while still being able to build up bigger tokens for the common patterns. Now let's look at the dog example. If you're not careful, then BPE will create a bunch of near duplicate tokens, like dog with a period, dog with an exclamation mark, and dog with a question mark. And it will represent all of these as different tokens. This wastes a lot of vocabulary space on what's basically the same word, dog. So what they did is they added a rule: don't let merging cross between different kinds of characters and letters versus punctuation, with one exception for spaces. So this keeps dog as one clean token instead of fragmenting it in 10 different ways. This input representation allows us to combine the empirical benefits of world-level LMs with the generality of byte-level approaches. Since our approach can assign a probability to any Unicode string, this allows us to evaluate our LMs on any dataset regardless of preprocessing, tokenization, or vocab size. So this is what they wanted from the start. Because this scheme can assign a probability to any string at all, they can test the model on any dataset, no matter how it was formatted or how it was cleaned. So they don't have to match the test sets pre-processing. And this kind of flexibility is extremely important because they're going to throw a lot of differently formatted datasets at this one model. We use a transformer-based architecture for our LMs. The model largely follows the details of the OpenAI GPT model with a few modifications. Layer normalization was moved to the input of each subblock, similar to a pre-activation residual network, and an additional layer normalization was added after the final self-attention block. A modified initialization, which accounts for the accumulation on the residual path with model depth, is used. We scale the weights of residual layers at initialization by a factor of 1 by root n, where n is the number of residual layers. The vocabulary is expanded to 50,257. We also increased the context size from 512 to 1,024 tokens, and a larger batch size of 512 is used. Okay. So the model itself is a transformer, the same family as the previous architecture paper, and it's mostly the same as OpenAI's GPT model with a few tweaks. The two changes that should be highlighted is that it can look back 1,000 tokens of context now instead of just 500. So it has more memory of what came before, and the vocabulary is about 50,000 tokens. The rest are kind of under the hood adjustments to keep training stable at a large scale. Let's take a look at table number 2, parameters, layers, and D model. So this table is the 4 model sizes that they built. 117 million parameters, 345 million, 762 million, and 1,542 million. The columns are how many layers deep each one is and how wide that D model number. So it's the same design but with 4 different sizes, and it gets taller and wider as you go down. Let's take a look at the experiments. We trained and benchmarked 4 LMs with approximately log uniformly spaced sizes. The architectures are summarized in table 2. The smallest model is equivalent to the original GPT, and the second smallest equivalent to the largest model from BERT. Our largest model, which we call GPT-2, has over an order of magnitude with more parameters than GPT. The learning rate of each model was manually tuned for the best perplexity on a 5% held-out sample of web text. All models still underfit web text, and held-out perplexity has as of yet improved given more training time. So they train all 4 sizes on log uniformly spaced, which just means evenly spaced when you think in multiples rather than straight addition. And all 4 models, they still underfit web text. Now, underfit means they haven't fully learned even the training data, and held out performance would still improve with more training. So the biggest one is not maxed out yet. They're showing you like a slope of the progression and not the finish line yet. Language modeling. As an initial step towards zero-shot task transfer, we are interested in understanding how web text LMs perform at zero-shot domain transfer on the primary task they are trained for, language modeling. Since our model operates on a byte level and does not require lossy preprocessing or tokenization, we can evaluate it on any language model benchmark. Results on language modeling datasets are commonly reported in a quantity which is a scaled or exponential version of the average negative log probability per canonical prediction unit, usually a character, a byte, or a word. We evaluate the same quantity by computing the log probability of a dataset according to a web text LM and dividing by the number of canonical units. For many of these datasets, web text LMs would be tested significantly out of distribution, having to predict aggressively standardized text, tokenization artifacts such as disconnected punctuation and contractions, shuffled sentences, and even the string, which is extremely rare in web text, occurring only 26 times in 40 billion bytes. We report our main results in Table 3 using invertible detokenizers, which remove as many of these tokenization/pre-processing artifacts as possible. Since these detokenizers are invertible, we can still calculate the log probability of a dataset, and they can be thought of as a simple form of domain adaptation. We observe gains of 2.5 to 5 perplexity for GPT-2 with those detokenizing. Okay, so the first test that they did, the first test is to check is it even good at its actual job, which is predicting text. And now they measure this with something called perplexity. So perplexity is a score for how surprised the model is by the real text. Low perplexity means the model found the text predictable, which is really good, and high perplexity means that it was surprised, which is bad. So for perplexity, a lower score is much better. Because a lower score means that the model was more confident and more correct. Okay, now one nice detail is the unknown token. The one that normal models use for words they've never seen shows up almost never in web text because the byte level scheme can spell almost anything. They also build reversible cleanup so that they can fairly score datasets that were formatted differently, and that alone buys them a few points of perplexity. Now let's take a look at Table 3. This is the results table for plain language modeling across 8 different datasets. The top row is the previous best, which is the state of the art. The bottom row, this one is their biggest model. And the thing to notice is on most of these columns, the bottom row number beats the top row. The bold numbers, these ones, are where they win. Transfer well across domains and datasets, improving the state of the art on 7 out of 8 datasets in a zero-shot setting. Large improvements are noticed on small datasets such as Penn Treebank and Wikitext2, which have only 1 to 2 million training tokens. Large improvements are also noticed on datasets created to measure long-term dependencies like Lambda and the children's book test. Our model is still significantly worse than prior work on the 1 billion word benchmark. This is likely due to a combination of it being both the largest dataset and having some of the most destructive pre-processing. 1 BWs, sentence level shuffling, removes all long-range structure. So they win on 7 out of 8 of these datasets. Big jumps come on small datasets like Penn Treebank and Wikitext2, which only have a tiny bit of training text, and on datasets that test long-range memory like Lambda and children's book test. They lose on those ones. Now, this is huge because it was pre-processed by shuffling sentences around, which destroys the long-range structure that their model is good at using. So these two datasets are just a bad match for how this model specifically works. Children's book test. The children's book test, CBT, was created to examine the performance of LMs on different categories of words, named entities, nouns, verbs, and prepositions. Rather than reporting perplexity as an evaluation metric, CBT reports accuracy on an automatically constructed closed test, where the task is to predict which of the 10 possible choices for a emitted word is correct. Following the LM approach introduced in the original paper, we compute the probability of each choice and the rest of the sentence condition on this choice according to the LM, and predict the one with the highest probability. As seen in Figure 2, performance steadily improves as model size is increased, and closes the majority of the gap to human performance on this test. Data overlap analysis showed one of the CBT test set books, The Jungle Book by Rudyard Kipling, is in web text, so we report results on the validation set, which has no significant overlap. GPT achieves this new state-of-the-art results 93.3% on common nouns and 89.1% on named entities. A detokenizer was applied to remove PTB-style tokenization artifacts from CBT. So this test, called the children's book test, checks whether the model handles different kinds of words, names, nouns, verbs. And the format is like fill in the blank. They give the model 10 options for the missing word, and the model scores each one and picks the most likely. So as the model gets bigger, it climbs towards human performance. And one of these test books, which is the Jungle Book by Rudyard Kipling, it just happens to be in web text. So they drop that one and they report on the rest to avoid scoring the model on something that it already knew. The Lambda dataset tests the ability of systems to model long-range dependencies in text. The task is to predict the final word of sentences which require at least 50 tokens of context for a human to successfully predict. GPT-2 improves the state of the art from 99.8 to 8.6 perplexity and increases the accuracy of LMs on this test from 19% to 52.66%. Investigating GPT-2's errors showed most predictions are valid continuation of the sentence, but are not valid final words. This suggests that the LM is not using the additional useful constraints that the word must be the final of the sentence. Adding a stop word filter as an approximation to this further increases accuracy to 63.24%, improving the overall state of the art on this task by 4%. The previous state of the art used a different restricted prediction setting, where the outputs of the model were constrained to only words that appeared in the context. For GPT-2, this restriction is harmful rather than helpful, since 19% of answers are not in context. We use a version of this dataset without pre-processing. Alright. So Lambda tests long-range memory, and the task is to predict the very last word of a passage, and these passages are built so that you need a lot of earlier context to get it right. At least 50 words back, which is what it says. Now the model takes the previous best from a perplexity of 99.8 all the way down to 8.6. Now remember that low perplexity is better, so this is a huge jump for this model. And the accuracy goes from 19% to 52.66%. Now the clever observation here is that they looked at all of these models' mistakes, and most of its wrong answers were perfectly reasonable continuations of the sentence, but it was just not valid as the final word. The model wasn't using the extra rule that the answer has to end the sentence. So they add a simple filter which doesn't let it guess the common filler word as the ending, and the accuracy jumps to about 63%. Winograd Schema Challenge. The Winograd Schema Challenge was constructed to measure the capability of a system to perform common sense reasoning by measuring its ability to resolve ambiguities in text. Recently, Trin and Lei demonstrated significant progress on this challenge using LMs by predicting the resolution of the ambiguity with higher probability. We followed their problem formulation and visualized the performance of our models with both full and partial scoring techniques in Figure 3. GPT-2 improved state-of-the-art accuracy by 7%, achieving 70.70%. The dataset is quite small with only 273 examples, so we recommend reading to help contextualize this result. Now the fourth one is the Winograd Schema Challenge. So this was the common sense reasoning test. Now, Winograd schemas are sentences which have an ambiguous pronoun in them, and you need to use the context around it to figure out what words like it or they refer to. Now, they resolve the ambiguity by checking which reading the model finds more likely, and the model, it says, pushes the state-of-the-art accuracy by from 7% to 70.70%. The conversation question answering dataset, COCA, consists of documents from 7 different domains paired with natural language dialogues between a question asker and a question answerer about the document. COCA tests reading comprehension capabilities and also the ability of models to answer questions that depend on the conversation history, such as why. Greedy decoding from GPT-2, when conditioned on a document, the history of the associated conversation, and a final token A, achieves 55 F1 on the development set. This matches or exceeds the performance of 3 out of 4 baseline systems without using the 127K plus manually collected question-answer pairs those baselines were trained on. This supervised SOTA, a BERT system, is nearing the 89 F1 performance of humans, while GPT-2 performance is exciting for a system without any supervised training. Some inspection of its answers and errors suggests GPT-2 often uses simple retriever-based heuristics such as answer with a name from the document in response to a who question. Alright, so this is the COCA result from the abstract, now given with a lot of details surrounding it. So COCA gives the model a document and a back and forth conversation of questions about that document. Here. Questions about the document. And this includes follow-ups that depend on earlier answers, just like asking questions like why. Now the way they get the model to answer it, they feed the document, then the conversation, then a final token that's literally A : for the answer. And then they let the model continue. That A is the prompt that says, okay, now it's your turn, answer now. Now this gets 55 F1. So 3 out of 4 baseline systems it matches or beats were trained on over 127,000 question-answer pairs. This model didn't see any of that. The current best system, which is a BERT-based one, it's nearly 89. Now this is nearly close to human performance. So GPT-2 is not just like winning on the task, but it's matching trained baselines without zero training. Now, when they look for answers, the model is often using simple tricks like for a who question, it just grabs a name out of the document. So it's not deeply reasoning, it's most like pattern matching, and it just simple retrieval based heuristics, so just answer with the name. So it's not just reasoning, it's more like pattern matching. We test GPT-2's ability to perform summarization on the CNN and Daily Mail dataset. To induce summarization behavior, we add the text TLDR after the article and generate 100 tokens with top K random sampling, with K is equal to 2, which reduces repetition and encourages more abstractive summaries than greedy decoding. We use the first 3 generated sentences in these 100 tokens as the summary. While qualitatively the generations resemble summaries as shown in Table 14, they often focus on recent content from the article or confuse specific details such as how many cars were involved in a crash or whether a logo was a hat or shirt. On the commonly reported Rouge 1-2L metrics, the generated summaries only begin to approach the performance of classic neural baselines and just barely outperform selecting 3 random sentences from the article. GPT-2's performance drops by 6.4 points on the aggregate metric when the task hint is removed, which demonstrates the ability to invoke task-specific behavior in a language model with natural language. To make the model summarize an article, what they do is they paste the article and then they add this TLDR after it and they let the model continue. Now, TLDR is usually like too long, didn't read, and online it's followed by a short summary. So the model has seen that pattern thousands of times in web text, and the TLDR acts like a switch that says, alright, summarize this now. And they didn't train the model to summarize. It's just a cue that already exists on the internet. Now, testing how good the model actually is at doing it, it's not that good. The summaries, they read like summaries, but they barely beat just picking 3 random sentences from the article. And sometimes the details are wrong. Like here it's given how many cars were in a crash or what the logo was. But when they remove this TLDR cue, the performance drops by about 6 points. So that little text cue, even though it doesn't work that well, it is what's switching on the summarizing behavior. The instruction, which is written in plain words, is actually doing the real work. Translation. We test whether GPT-2 has begun to learn how to translate from one language to another. In order to help it infer that this is the desired task, we conditioned the language model on a context of example pairs of the format English sentence equals French sentence. And then after a final prompt of English sentence equals, we sample from the model with greedy decoding and use the first generated sentence as the translation. On the WMT14 English-French test, GPT-2 gets 5 blue, which is slightly worse than a word-by-word substitution with a bilingual lexicon inferred in previous work on unsupervised word translation. On the WMT14 French-English test, GPT-2 is able to leverage its very strong English language model to perform significantly better, achieving 11.5 blue. This outperforms several unsupervised machine translation baselines from Artext and Lample, but is still much worse than the 30.5 blue of the current best unsupervised machine translation approach. Performance on this task was surprising to us, since we deliberately removed non-English web pages from web text as a filtering step. In order to confirm this, we ran a byte-level language detector on web text, which detected only 10 MB of data in the French language, which is approximately 500 times smaller than the monolingual French corpus common in prior unsupervised machine translation research. Okay. Now, translation is all about the prompt that it's given. So to get a translation, they first show a model a few example pairs in the format that English sentence is equal to French sentence, and then they write English sentence equals to, and then they let the model fill in the French. Now these examples teach it the pattern on the spot without any prior training. Now on English to French translation, GPT-2, it gets 5 blue, which is very, very low. And on French to English, it gets 11.5 blue, which is better but still kind of much behind dedicated systems for this. Now, they deliberately removed non-English web pages from web text, and so they went back and measured how much French was left, and it was only about 10 megabytes of data they used for French translation. But it still picked up some of the translation ability from only this much data. So this is a surprising result for such little data that they had to use. Question answering. A potential way to test what information is contained within a language model is to evaluate how often it generates the correct answer to factoid-style questions. Previous showcasing of this behavior in neural systems, where all information is stored in parameters such as a neural conversation model, reported qualitative results due to the lack of high-quality evaluation datasets. The recently introduced natural questions dataset is a promising resource to test this more quantitatively. Similar to translation, the context of the language model is seeded with example question-answer pairs, which helps the model infer the short answer style of the dataset. GPT-2 answers 4.1% of questions correctly when evaluated by the exact match metric commonly used on reading comprehension datasets like SQuAD. As the comparison point, the smallest model does not exceed the 1.0 accuracy of an incredible simple baseline, which returns the most common answers for each question type: who, what, where, etc. GPT-2 answers 5.3 times more questions correctly, suggesting that model capacity has been a major factor in the poor performance of neural systems on this kind of task as of yet. The probability GPT-2 assigns to its generated answers is well calibrated, and GPT-2 has an accuracy of 63.1% on the 1% of questions it is most confident in. The 30 most confident answers generated by GPT-2 on development set questions are shown in this table 5. The performance of GPT-2 is still much worse than the 30 to 50% range of open domain questions answering systems which hybridize information retrieval with extractive document question answering. Okay. So the last task that they tested this model on is factual questioning answering. The idea is you can probe what facts the model has absorbed just by asking it random trivia. It's the same method as the translation, but they prime it with a few question-answer pairs so that it learns the short style, like the short answer style. Then they ask a new question following that. Now the biggest model gets about 4% of these exactly correct, Now, this sounds kind of terrible until you compare with the other ones. The smallest model barely beats a dumb baseline that just guesses the most common answer. So going from small to big multiplies the score by more than 5. And so size of the model is clearly driving this. Let's take a look at table 5. It's the 30 questions the model was the most confident about, and it nails most of them. Like, who wrote the book The Origin of Species? Who is the founder of the Ubuntu project? The questions it's more sure about, the top 1%, it's right about 63% of the time. So when it's confident, it's often correct. It just isn't confident that often. All right. Generalization versus memorization. Recent works in computer vision has shown that common image datasets contain a non-trivial amount of near-duplicate images. For instance, CFAR10 has 3.3% overlap between train and test images. This results in an over-reporting of the generalization performances of machine learning systems. As the size of datasets increases, this issue becomes increasingly likely, which suggests a similar phenomena could be happening with web text. Therefore, it is important to analyze how much test data also shows up in the training data. To study this, we created Bloom filters containing 8 grams of web text training set tokens. To improve recall, strings were normalized to contain only lowercase alphanumeric words with a single space as a delimiter. The Bloom filters were constructed such that the false positive rate is upper bounded by 1 by 10 raised to 8. We've further verified the low false positive rate by generating 1 million strings, of which 0 were found by the filter. Okay. Now they point out that this isn't a new problem. In image data sets, the training and test sets, sometimes they share duplicate images, which makes the model look better than they actually are. So they check for the same thing inside of web text, and they do this by using a tool called Bloom filters. Now, Bloom filter is just a fast, memory efficient way to ask, have I seen this little chunk of text before? And they fill it with 8-word chunks or 8 grams from their training text, and then they can check any data against it. Now, an 8 gram is just a sequence of 8 consecutive words, and a Bloom filter is a fast lookup structure that can tell you if something is probably inside a set. These Bloom filters let us calculate, given a dataset, the percentage of 8 grams from that dataset that are also found in the web text training set. Table 6 shows this overlap analysis for the test sets of common LM benchmarks. Common LM datasets test sets have been between 1 to 6% overlap with web text train with an average of overlap of 3.2%. Somewhat surprisingly, many datasets have larger overlaps with their own training splits with an average of 5.9% overlap. Now, this is the result if we take a look at table 6. They measure for each test set what percent of its 8-word chunk also appears inside of web text. Now, the overlaps are pretty small. Mostly it's just 1 to 6%. But these test sets overlap with their own official training sets even more, almost 6% on average. So web text isn't unusually contaminated. The amount it shares with the test is about the same as or less than the contamination that those benchmarks have already built in. Alright. Our approach optimizes for recall, and while manual inspection of the overlap shows many common phrases, there are many longer matches that are due to duplicated data. This is not unique to web text. For instance, we discovered that the test set of Wikitext 103 has an article which is also in the training data set. Since there are only 60 articles in the test set, there is at least an overlap of 1.6%. Potentially, more worryingly, one BW has an overlap of nearly 13.2% with its own training set according to our procedure. For the Winograd schema challenge, we found only 10 schemata which had any 8-gram overlaps with the web text training set. Of these, 2 were spurious matches. Of the remaining 8, only one schema appeared in any context that gave away the answer. For COCA, about 15% of documents in the news domain are already in web text, and the model performs about 3 F1 better than these. COCA's development set metric reports the average performance over 5 different domains, and we measure a gain of about 0.5 to 1.0 F1 due to overlap across the various domains. However, no actual training questions or answers are in web text since COCA was released after the cutoff date for links in web text. On Lambda, the average overlap is 1.2%. GPT-2 performs about 2 perplexity better on examples with greater than 15% overlaps. Recalculating metrics when excluding all examples with any overlap shifts results from 8.6 to 8.7 perplexity and reduces accuracy from 63.2% to 62.9%. This very small change in overall results is likely due to only 1 in 200 examples having significant overlap. Now they go dataset by dataset and they basically say the overlap exists, but it's very small and it's consistent throughout, but it gives a minor boost in the results. For example, on Lambda, redoing the scores without the overlapping barely moves anything. Overall, our analysis suggests that data overlap between web text training data and specific evaluation datasets provides a small but consistent benefit to reported results. However, for most datasets, we do not notice significantly larger overlaps than those already existing between standard training and test sets, as Table 6 highlights. Understanding and quantifying how highly similar text impacts performance is an important research question. Better deduplication techniques such as scalable fuzzy matching could also help better answer these questions. For now, we recommend the use of n-gram overlap-based deduplication as an important verification step and sanity check during the creation of training and test bits for new NLP datasets. Another potential way of determining whether the performance of web text LMs is attributable to memorization is inspecting their performance on their own held-out set. As shown in Figure 4, performance on both the training and test sets of web text are similar and improve together as model size is increased. This suggests even GPT-2 is still underfitting on web text in many ways. GPT-2 is also able to write news articles about the discovery of talking unicorns. An example is provided in Table 13. Okay. They give the cleanest argument that there's a second way to check if it's just memorization by looking at, does this hold its own on text from the same web text pool that it never trained on? And so in Figure 4, where is this? Okay. In Figure 4, the training and the held out performance go up together as the model grows. If it were memorization, these two lines would split apart and the model would ace what it saw and flop on what it hasn't seen yet. But it didn't do that, and these two lines, they move together. So this is strong evidence that it's actually learning patterns and not just storing answers and reusing them. Now this last line, GPT-2 is able to write news articles about the discovery of talking unicorns, is pretty famous. They say that the model can write a news article about the discovery, and they put the example in the back of the paper. This is the sample that made GPT-2 go viral. It made up a coherent, totally fake news story about unicorns in the Andes, and it reads like a genuine article. So let's skip past related work. The main neighbor of work is just asking the same question: what happens when you make language models bigger and train them on more data? And other people scaled up models on big benchmarks and studied what they learned and how to evaluate the representations that they built, and showed that pre-training on language helps a lot of downstream tasks. Let's go ahead and read discussion. Much research has been dedicated to learning, understanding, and critically evaluating the representation of both supervised and unsupervised pre-training methods. Our results suggest that unsupervised task learning is an additional promising area of research to explore. These findings potentially help explain the widespread success of pre-training techniques for downstream NLP tasks, as we show that, in the limit, one of these pre-training techniques begin to learn to perform tasks directly without the need for supervised adaptation or modification. Now the discussion is them stepping back, and their results suggest that unsupervised task learning, just learning tasks from raw text, is a promising direction worth exploring, and it helps explain why pre-training works so well in general. In the limit, a model that's just predicting text well enough starts doing tasks directly with no task-specific training. That's the thesis restated now as a takeaway. On reading comprehension, the performance of GPT-2 is competitive with supervised baselines in a zero-shot setting. However, on other tasks such as summarization, while it is qualitatively performing the task, its performances is still only rudimentary according to quantitative metrics. While suggestive as a research result, in terms of practical applications, the zero-shot performance of GPT-2 is still far from usable. We have studied the zero-shot performance of web text LMs on many canonical NLP tasks, but there are many additional tasks that could be evaluated. There are undoubtedly many practical tasks where the performance of GPT-2 is still no better than random. Even on common tasks that we evaluated on, such as question answering and translation, language models only begin to outperform trivial baselines when they have sufficient capacity. Now, they lay out where it actually stands. On reading comprehension, the zero-shot model is competitive with supervised systems, but on summarization, it's only doing the task in a rough surface-level way. The numbers are pretty weak on this. They say plainly that the zero-shot performance is still far from usable for a lot of real applications, and there are many tasks where it does no better than random. So it's a research result that points somewhere exciting, not a finished product. And they say this pretty directly. While zero-shot performance establishes a baseline of the potential performance of GPT-2 on many tasks, it is not clear where the ceiling is without fine-tuning. On some tasks, GPT-2's fully abstractive output is a significant departure from the extractive pointer network-based outputs which are currently state-of-the-art on many question answering and reading comprehension datasets. Given the prior success of fine-tuning GPT, we plan to investigate fine-tuning on benchmarks such as DECA NLP and GLUE, especially since it is unclear whether the additional training data and capacity of GPT-2 is sufficient to overcome the inefficiency of unidirectional representations demonstrated by BERT. They end the discussion by pointing forward. Everything here was zero-shot, it didn't have any fine-tuning. And they said they didn't know how high this could actually go if you did fine-tune it, and they plan to try that on the standard benchmarks. They specifically wonder whether GPT-2's extra size and data could close the gap with BERT. So they're flagging the next experiment already. Conclusion: when a large language model is trained on a sufficiently large and diverse data set, it is able to perform well across many domains and data sets. GPT-2 zero shots to state-of-the-art performance on 7 out of 8 tested language modeling datasets. The diversity of tasks the model is able to perform in a zero-shot setting suggests that high-capacity models trained to maximize the likelihood of a sufficiently varied text corpus begin to learn how to perform a surprising amount of tasks without the need for explicit supervision. When you train a large enough language model on a large enough pile of text with enough variation in it, it learns to do well across many domains and tasks, zero-shot, with no task-specific training. Now, the diversity of stuff it can do suggests that a big model, which is just trying to predict varied text, starts learning to perform a surprising number of tasks on its own with no explicit supervision. So this is the GPT-2 paper. Thank you so much for reading this with me. Thank you.